Hey guys, welcome back. And in this video we're going to talk about how to solve logarithmic equations, somewhat similar to what we did in our last video with exponential equations. And then towards the end of the video we're going to introduce some different type of growth problems that will help us to transition into the final lesson for our unit next video, which will be on interest formulas. So we talked about exponential equations in our last video, how to solve them algebraically and graphically, and we're going to see that the same rules apply for solving logarithmic equations, just in reverse. So you're still going to isolate the base that you have with either the exponent or logarithm that it goes along with by opposite operations. Then rewrite your problem. Now in this case it'll be from a logarithm to an exponent. Think of how whenever you write an addition problem and you want to switch it, okay, you want to move something that's addition from one side to the other, you do that by opposite operations. Subtraction, it'll be the same thing here. Opposite of a logarithm will be an exponent. Then you will have to isolate the given variable that you have, x or y or whatever, and then approximate your solutions sometimes. Sometimes you do have to round them, and we'll talk about that. And then finally, double check your solution by graphing it. For example, if I had an equation written out like this, log base 3 of 2x minus 5 plus 8 equals 12, you would set both sides equal to y, graph both sides individually, and then in Desmos, zoom out if you need to, but find if they have a point of intersection. So wherever the two graphs that you'll have will cross, okay, that x-coordinate will be your solution to the problem. In this example, you could check it yourself. It'll be at x equals 43. And if they don't intersect, then you have no solution. So let's take a look at solving a problem here algebraically on the board on the left side. And this is a special logarithm. This is the natural log, right? ln, lowercase l, lowercase n, standing for log, natural or natural logarithm. And if we want to try to solve for x, we need to get the logarithm and that parentheses by itself on one side of the equation. Now, sometimes it's already that way. In this case, it's not, right? We have a plus 3 to the left side of the equation, not part of your logarithm. We need to get rid of that. Opposite operations. Now our logarithm will be by itself on the left side of our equation. And we can proceed. We can start to rewrite our problem. Now in this case, special logarithm will change to a special base. Okay. Base will stay special. Everything else will switch sides. So this is kind of that principle. The base stays the same, everything else switches. Special logarithm turns to a special base for an exponent. And that exponent will now be a 3 because it started on the right, moves to the left. X minus 9 moves from the left to the right. And finally, adding this number to both sides allows us to solve for x. Now, if I was to approximate this, and I'd have to go back and look, but I think this is something, if you were going to simplify it in a calculator, something like 29.08 or 06 or something like that. But this is an approximate answer, right? Whatever this turns out to be, you're going to have to round it is the point. And because you do have to round this to a certain decimal, what will happen if you try to plug this back into your original problem is, okay, the left side will be very close to 6, but it might be a little bit more than that or a little bit less than that. Again, this is an approximation. So it's going to approximate back to this original equation. This actually right here is more exact. E cubed plus 9. That's the more precise answer. This is the approximate decimal answer. This is still important or useful because, like we mentioned before, if you graph the left side of the equation and then the right side of the equation, setting both of those sides equal to y, it's going to turn out that they're going to intersect or cross. Those graphs will cross at approximately this coordinate point. Now, that will also be a rounded coordinate point as well, but that is sufficient for our purposes, and that is how you approach solving and double checking a solution that is something approximate or estimated. Okay, so I believe the answer is something like that. Check for yourself, what is e cubed plus 9? Whatever you round that to should match what happens when you graph both sides of your original equation. Let's take a look at a word problem as well, though, because not everything is set up to where you can graph it immediately. This, you can easily graph the left and right side of your equation. Here, however, we have a real-world scenario where we have two variables, and when we have that scenario, we can't really graph both sides of the equation, at least not immediately. So we have a situation in which earthquakes have a certain magnitude on the Richter scale, depending on the amount of kilowatt energy hours that is released, kilowatt hours of energy that is released. And in this case, magnitude refers to R, and kilowatt hours of energy refers to X. So we're going to ask two different questions and try to solve individually for those variables given different questions. So if an earthquake releases 10 kilowatt hours of energy, you stop right there. All right, what are we looking at? 10 kilowatt hours of energy refers to what? What variable? And hopefully going back to your problem, you see that it refers to X. Okay. X equals 10, in other words. And we're trying to solve or find R, the magnitude. So we don't know what that is. Okay. Now in this problem, what you'll notice, 3.5 times X, we're going to replace that with a 10, as our equation asks us to plug that in. What you'll notice is that you can actually calculate that with a calculator immediately. Okay. Don't remember what the answer is here. I think it's something like a 6, or maybe a 3. Let me double check real quick. But you don't have to use the change of base formula here. Instead, yeah, 3.9 will be the result here. Will be the magnitude. What I was mentioning was we don't have to use the change of base formula in this problem because the base is actually an invisible 10. Okay, we mentioned in a previous video that if you have a specific base, something other than 10, then to calculate that, you need to use the change of base formula. Okay, base b, bottom b of logarithm division. In this problem, actually, we don't have to change anything. Okay, that logarithm is already set to the default that our calculator works with in the first place. So we can actually calculate this immediately. As you saw me type it in, I didn't need to use the change of base formula. Neither do you. Test that on your own in Desmos. You should get the same answer there for the magnitude of the earthquake. The second question here is going to reverse the variable that we're looking for. So now we know that we have a 6.5 on the Richter scale. R is 6.5. And what we'll be looking for is X. How many kilowatt hours of energy have to be released in order for us to reach that magnitude? Solve for X, okay, in other words. So, same process that we've used in the past. Subtract by 2.5, that's not part of your logarithm, right? Isolate your logarithm by itself. And then once again, this 2 that you're multiplying in the front, that also is not part of your logarithm. So you also need to, opposite operations, divide 2 to both sides. Okay, 4 divided by 2 is 2. And this is where it's very important. Remember, your base there, some students can get confused. It's better to write this out, make that base visible. It's a 10. Okay. Why is that so important? because we're about to use our rewriting formula. The base stays the same and everything else switches. So in this case, the base is a 10. 10 stays the same, 10 stays where it is. Everything else switches sides, and now we have an exponential equation. So 2 started on the left, moved to the right, 10 squared. 0.5x started on the right, will move to the left. Simplify a little bit here, we get 0.5x equals 100. 10 squared is 100. And then lastly, divide by 0.5, right? We're multiplying. Opposite of that will be divide to get x by itself. That's going to equal 200 kilowatt hours of energy. Okay. The key thing there, though, was to remember that your base was an indivisible 10. That's the only way that you're going to be able to rewrite the problem in order to solve. So if you plug 200 back into x, right, in your original equation here, and multiply this out, it will equal a 6.5, and that's how you can double check that you have solved that correctly. So that is how to solve logarithmic equations. Double check yourself by graphing where you can, or take whatever answer you get, plug it back into the original equation you started with, double check that both sides balance. Same thing that you would do with exponential equations and solving those, except in this case you are solving logarithms, but the steps are very similar. Okay. One other thing I wanted to cover in this video were some growth problems, and this is going to be somewhat of a transition into our last video, like I mentioned, our last lesson, which will be upcoming shortly. But I want to go over, once again, the idea of what is exponential growth versus exponential decay. How does that look? And do so in the context of a table. I know that we've looked at this with graphs and with a base that is bigger than 1, it's going to be exponential growth, or a base of an exponent is less than 1, it'll be exponential decay. Which of these tables, if we had a zombie apocalypse, which of these tables would depict exponential growth occurring over time? So what we would want to do is go through, okay, day 0, there's 1 zombie. Day 1, there's 3 zombies. Day 2, there's 7 zombies. So on and so forth. Read it that way. And then think, does this describe exponential growth? And in this case, the answer is no. This is not exponential growth. Yes, the number of zombies do increase over time, but not in any discernible pattern, right? They go from 1 to 3. So it looks like we're multiplying by 3 here. But then 3 times 3 is not 7, right? We're adding by 4 in this case. And then we're adding by 5 zombies the next day. And then we're adding somehow by 17. There's no discernible pattern here. This is not exponential growth. This is just growth over time. It is increasing, that's true enough, but it's not exponential increase. Okay. Another example of what would not be exponential growth would be here, where day 81, it looks like we're actually counting backwards. Okay. Day 81, there's 4. Well, that doesn't seem like there's many zombies there. Day 27, there were 3 zombies. Day 9, there were 2. Day 3, there were 1. Day 1, there were 0. Definitely not growing over time, besides increasing by 1, right? If we want to start looking at it in reverse, yes, on day 1 there's 0 zombies, and then it took us a long time, 2 days for it to be 1 zombie, and then 6 days later there's another zombie, and then so on and so forth. Okay, that's not exponential growth. Definitely not, because it's not increasing rapidly. The only example of exponential growth is what we see here in the middle. Okay, and why is this counted as exponential growth? Well, number 1, we are increasing each day. We have more zombies, right? But also, we're increasing by the same rate. Okay, multiplying by 3 each time. The base is 3. We're multiplying by 3 each day sequentially, and we could create an exponential equation that matches this. Y equals 3 to the power of x. Okay, on day 0, 3 to the power of 0 is 1. How about after day 1? 3 to the power of 1, day 1, we'll have 3 zombies. Or after 2 days, 3 squared is 9. Or 3 cubed will be 27. Or 3 to the 4th power will be 81 zombies, okay? So we do have one exponential growth problem, this one. And that's because the base is bigger than 1. You're multiplying by 3 sequentially each day. You're not just increasing in general, you're increasing exponentially. Okay, so that's one type of growth that you will need to be able to know based on a table. And then one other type of growth I want to discuss is hourly rate. So let's say that we have a culture of bacteria that, key word here, quadruples each hour. So let's take a look at what happens by 4 p.m. There's 896 bacteria. Now, if I wanted to go, and the easiest way to do this, because we're going to look for how many bacteria were at 1 p.m., how I would set this up, and I've seen some students do this as well, is to just go ahead and write out some of these hours, right? The hourly rate is increasing, so we're going to work with hours here. Okay. Now we have 896 okay, at the end of 4 p.m. If I wanted to quadruple that going forward, what that would mean is, think about if you doubled your money, you'd multiply it by 2. If you tripled money or bacteria, you'd multiply it by 3. If you quadrupled it, you're multiplying by 4. I would want to multiply by 4 going forwards in time. Each hour later, it quadruples, it multiplies by 4. But if I'm going backwards in time, if I'm looking back to where 1 p.m. is, okay, I'm dividing. I'm doing the opposite of multiplying. Everything multiplies forward in time. That must mean it divides if we look backwards in time. In other words, if I want to know from 4 p.m. to 1 p.m. where I started, I have to divide 896 by 4 to get to 3 p.m. first. And that'll be, that's 224. Okay. That takes me back to what was the count at 3 p.m. 224 times 4 will be this, 1 hour later. If I want to get back to 2 p.m., I have to divide by 4 again. And that looks like it's going to be 56 bacteria. Again, if I multiply forwards, it gets me to the next hour down. But we're working backwards, so we're dividing. And lastly, 56 divided by 4 is what we're looking for here. And that'll be 14 bacteria. Okay. Opposite of quadrupling, opposite of multiplying by 4, going back in time is dividing by 4. 14 bacteria. So a lot of the problems that we're going to be dealing with moving forward are going to be real-world scenario based, which will hopefully make it a lot more relevant and interesting to you guys out there. Come back for our last video on interest formulas. There's going to be a lot of good information that is going to be really relevant for you, not just now, not just in Algebra 2, but post-high school. So I hope to see you then, and I hope this helped you.